Okay, AP Environmental Science. This is chapter 23, Minerals and Mining. Kind of a geology chapter, but more of an application of what we're going to do. Most of us won't get involved in this, but when you see the applications of where these things go, I think it will help you see your modern context a little bit differently. We'll talk briefly, and this is only like a 16-minute lecture, so I'll leave it up for a couple, 3 days that you can use for your attendance. But we're going to look at defining what minerals are and mostly focus on how they're extracted. But then the modern application that I want you to see is primarily for electronics, and then what happens to the environment after we have pulled precious minerals or trace minerals out for use. And so that's the big deal. And so your book starts off with this conflict in 1998 about cell phone applications and minerals being fought over because this one place has a rich deposit. And unfortunately, it was in the Congo, which requires a clearing of a lot of area, which you're going to learn about mining. There's a lot of material that has to be removed for a very small amount of material that's quite expensive. Lauren Scott, that is not a quagga. I thought it would be funny if it was when I first saw that creature, but it's an okapi. It's a relative of a giraffe. But there's a shout out to Lauren to see if she emails me and mentions the word quagga. But nevertheless, the expense and the cost and the toll on the natural environment to remove so much material to get so little is really, really intense. No one really knows a solution for this, but believe it or not, underground black markets have emerged for competition for these types of things, and tech companies are the ones that need them the most. One of the things that you'll see in this next picture is where these minerals, these elements go. And so there's a simple cartoon picture. Most of what you're looking at is electronics, besides the Coke can there that he's holding. But it even goes into our dry erase boards, our markers, and of course our electronics, synthetic materials that are not made of plastic. It is phenomenal as I went through this chapter where how many common substances are made from rare and precious minerals. So there's your definitions of a rock versus a mineral. Usually you're talking about something that has a chemical purity to it. It's an inorganic compound. It could be crystalline in structure or just a straight up element, untainted or unmixed. But there's rock versus mineral. Whereas the act of extracting this stuff is called mining. We have gotten really good since the Industrial Revolution of systematically filtering, extracting, and removing the stuff we don't want to go for the stuff that we do want. We started learning how to do that with water underneath the ground. Then we started using fossil fuels like coal, gas, petroleum. Natural gas. We got, petrol, gas, and petroleum. No, golly, stop. Gas and petroleum, as well as coal. We got really good at that. And now we apply it to rare minerals. This picture indicates how much one person will use during their lifetime, which is a staggering amount given in the modern context, whether it's used for construction of an office, a home, a car, electronics, you name it. Not just what we're going to eat, but what we'll actually use and consume. Metals like iron ore, steel, and precious metals used for electronics is what most people are after if we're going to talk about the 21st century. Coal is still used, but not for transportation, not so much anymore in manufacturing. But anyway, anytime you get these things, they are always mixed with something, so they have to be pulverized to increase their surface area to volume ratio. They're heated to separate them according to light and heavy metals and burn off any impurities. And then what ends up happening is that they make a new type of substance called an alloy that they can, I don't know, maybe it's more malleable or more durable, and they'll use it for other applications that we need. And so a lot of these are water intensive and energy intensive. If you can imagine how hot you have to get a furnace to melt iron ore and keep it that way, that is extremely dangerous as well as expensive. And so nothing is cheap here. What you don't use, you then have to ask, what do you do with it? I mean, a lot of the smelting pollutes the air. And then when you get rid of the stuff you don't want, you can't just put it back. You have to do something with it, and it's concentrated and taken out of its natural context. So you'll have these large reservoirs called surface impoundments where they basically try to water it down. That helps contain and change the pH a little bit, but they can't just release it back in the wild. So basically, they just let it leak. When it comes to things that are not so precious, this is just a couple slides to show you what happens with these these substances, like what's made for concrete, basically. Your granite countertops, limestone, and some of your nice buildings and gems. Just as expensive, but the cost per unit is really high to sell this stuff. And so this map just shows you where most of the types of minerals are found in the world, which will lead to greater opportunity, greater economy, and greater conflict, all in the same context. I will put some of these review questions up on a pod for this lecture, so just note the question here, see if you want to write down an answer, and when you get to it later, maybe I'll make it into a separate lecture quiz pod. We'll see, but you can know what you want to say there. It won't take you as long. So the real problem is not so much that we use minerals or how much we want to possess them, but really the issue is the methodology of extracting them from the earth. Consider them precious, meaning rare minerals, but we need large amounts of them. Again, even if you think about the use in technology, and so we have to get rid of all the stuff we don't want to get it out of the way to get to the stuff we do want. And so one of the common methods is strip mining, which basically means removing layer by layer by layer to get down to the level or layer that you want, and therefore you can remove it. You think you could put the stuff back, but you can't put it back obviously the way you got it out. And so basically these areas are exposed for a long time, and exposure, not to mention deformation of the actual land, is the issue. So exposure and deformation will be the main two concerns. Once things are exposed and that topography is changed, you are going to have all kinds of problems with drainage. These are, I don't know if you remember your stuff from chemistry, but these are mostly salts that can leach into freshwater systems and they become acidic. They react with oxygen that they were not exposed to and then create all kinds of acids, mostly sulfuric in this context. Other ways you could do this is mining. You know what mining is. This is a high risk job just because of collapse, low oxygen, and exposure to natural gas. And so things can blow up, things can collapse, things can suffocate, and just incredibly dangerous line of work. But basically you're pulling it out bit by bit. This is a terrible picture in my opinion, where they talk about after mining is done, and you got this little girl running across this area full of sidewalk chalk, looks like, and the context here is that it can create a sinkhole and she can fall into that. And so I guess it's common enough to put it here, but it just seems like a terrible idea and a terrible picture with a child playing. But you have heard of some of this happening in the East Coast when freeways collapse and houses collapse. So open pit mining is exactly what it sounds like, just a giant hole in the ground. And when you see the next slide in just a minute, and it's in your book, I cannot fathom the scale of what it takes to remove that much material to get at the things that you want to get at. But we are able to do that due to our fantastic technology. But we are only extracting a very tiny amount compared to the total amount of mass that's being removed. In an open pit system, once that extraction is done, you basically have a giant bowl which fills up with water. That water is not even remotely safe. The same issue comes up again with the formation of acid. It's toxic. You can't let it leave. And it is full of all these metals, minerals, and compounds that it would not have had contact with because it was locked up in bedrock. And so look how low that pH can get, 2.2. That is almost hydrochloric. level of acid. And so in your videos, you learned about mountaintop mining. You don't have to dig down, you just shave off the top. It's safer, it's easier, but basically you are doing exactly what it sounds like. You are cutting off the top of a mountain, which is impressive and frightening all in the same context. And so this will change runoff, where water goes, not just that it goes. And certainly you have to remove vegetation, which removes topsoil, which removes animals, and so on and on it goes in a domino effect. And so I am surprised this is still done, but I guess someday the Appalachian Mountains will not be the Appalachian Mountains. They'll just be the hill country or something. Not sure. Looks pretty ugly to me, and I had no idea that that was a common practice, but I do now. So coming on down, we're almost done here in just a few minutes. You get this placer mining, which is smaller, lighter, separate, and you're just looking usually for precious minerals. And it's a tiny practice, but if you get enough people involved, it can aggregate and you can get quite a bit done. It keeps things in place. It's slower, and you don't have as many um, negative effects leached into fresh water. But I personally don't want to do solution or place mining for uranium. I would be fine with salt and copper, lithium maybe, but that is not a fast process. But apparently it's pretty lucrative for some of these folks in their locales. Seawater and mining in the ocean is a unique process. There are some serious videos on this and what it's like to go that deep down to extract this stuff. And they use basically giant hoses the size of probably our room to extract and dredge the ocean floor. You're going to lose a lot of marine life that's down there, and a lot of unique scenarios, but that's something that happens. You don't have to dig, you just suck it up because it accumulates on the bottom anyway. So most of what's happening now is reclamation, trying to restore an area to what it once was, removing all the artificial structures, bringing animals back and filling them in. It will never be what it once was, but I think this is a better practice rather than just leaving it once you're done. So since I was 3 years old and 77, this has been going on, and so evolution always allows life to continue, and so you have new types of creatures that can tolerate these terrible conditions and even clean up some of the acidic contexts like sunflowers and cattails. So they're really good at doing that. I think it's hilarious that our mining policy today in the 21st century, like you saw or will see in that one video, is still guided by a 19th century law. And so if you own a piece of land and your family owns a piece of land, you can mine it and you can tear it up and you can do all this stuff to it. And I guess, make some money. So I'm hoping that sustainability for this type of stuff just means reducing leaching, reducing acidic runoff, reducing waste, not tearing up the biosphere while you're doing it or while whoever's doing it. But it seems like a pretty aggressive process to me. Some minerals are really, really abundant. Some are going to run out pretty quickly. Just depends on what you're talking about. And this graphic that will probably be a data cue in your book just tells you where these things go and what they're used for. Screens alone, I think that's pretty telling that they're going to last only another 30 years. Recycling of electronics, if you want to know a cutting edge job, needs a lot of development. So here are the factors that go into the availability of what we're going to need over the next few decades. And so that will basically be when y'all are my age. And so if you find a way to extract easier and nicer and find a way to recycle, I think you'll be plenty wealthy if you can contribute to that in any way. So currently, only about 35% of the metals in the U.S. are part of are recycled out of our waste stream. That if you do the reverse, what is that? 65% are thrown away, and probably at a really drastic rate, given how much people like to keep up with modern tech. So the recycled minerals that you see in the US are here, but you can see the percentages. I think the only one that really tops 50% or near the top there, iron, steel, scrap, lead, and tungsten. But once you get past that, it goes way down. So this chapter, this lecture ends with a challenge to you and bringing it in the 21st century of how we can recycle our electronics. I just want to point out, as your chapter very well pointed out, that that is where the effect for sustainability and the concern needs to be. Honestly, keep your cell phone as long as you can. Um, it doesn't matter how many cameras it has or whatever, but that's your gig. But I say keep the electronics as long as possible. So there's two review questions that you'll see pop up here. Again, while I finish, I'm going to make a pod out of this. I will leave it up probably for 3 days, and you may use it for your attendance purposes. So you can watch it in parts and access it the next day and kind of fast forward it to where you left off. Just write that down, whatever minute and second you left, and just use it as though we were in class. You don't have to do it all in one setting. The entire lecture is about 16 and a half minutes to get it all done, but you can divide it up. All right, gang, that's it. I'll let you look at these questions and I'll talk to you later.